Yes. So let us see the next topic in this chapter, laws of motion. Maybe this may be the last topic in this chapter. That is about the center of mass. Already we have seen the concept of center of mass last time. And we have seen that the center of mass of two particles always divides the line joining them in the inverse ratio of their masses. तो ये हमने ऑलरेडी देखा था और उसके ऊपर कुछ एग्जांपल्स भी हमने ऑलरेडी सॉल्व किए थे किस तरह से ये बात हमको यूज करनी है और उसके लिए हमने दो फॉर्मूले भी डिराइव किए थे R1 and R2 which are for finding the center of mass of two particle system, the distance of center of mass from the two particle system from two particles, that is R1 and R2. तो ये दोनों R1 और R2 निकालने के लिए फॉर्मूले भी हमने डेवलप किए थे और लर्न किए थे. Yes, so let us move further in this chapter. अभी इसमें हमने लास्ट लेक्चर में ये ऑलरेडी देखा कि the center of mass of two particle system always divides the line joining them in the inverse ratio of their masses. और इसका भी बेसिस जो है तो हमने ऑलरेडी देखा था कि जो हमने 8th स्टैंडर्ड से सीखा था, effort arm into effort, or you can say effort into effort arm is equal to load into load arm. ये बात हम यहाँ पे समझ सकते हैं. And this can also be proved by using the condition of equilibrium. ठीक है ना, कंडीशन ऑफ इक्विलिब्रियम, रोटेशनल इक्विलिब्रियम का जो कंडीशन है तो वो अगर हम अप्लाई करेंगे यहाँ पे तो इससे हमको ये बात मिल जाएगी M1 R1 is equal to M2 R2, no doubt. And now we can just use this fact in order to find out the center of mass of multiple particle system. Okay, now we just focus on finding the center of mass of three particle system. But before that, we'll just try to apply this formula if suppose the coordinates of those particles are given. Okay, so let us see how to find out the center of mass of two particles once again. In terms of their coordinates. Okay, अगर उनके coordinates अगर दिए हैं XY coordinate system में, अगर उनके coordinates हमको दिए जाते हैं तो ऐसे केस में उनका center of mass कैसे ढूंढ के निकालने का तो वो हम देखेंगे. ठीक है. Okay, so let us try to find out. So let us consider this x-axis and y-axis here. तो ये समझ हमारा y-axis है और यहाँ पे ये x-axis है. And suppose there are two particles whose masses are given already and also their locations are given. That means अभी देखो कोई भी particle का XY coordinate system में location कैसे देंगे तो उसके लिए हमको उसका coordinate देना पड़ेगा. So suppose that this is the one first particular point. We can call it as A, whose mass is given to be M1, and suppose that its coordinates are given to be x1 y1. So ये A, that is x1 y1, these are the coordinates of this first particle of mass M1, which is located at point A here. Okay, let us consider another point B here. तो यहाँ पे एक दूसरा पॉइंट हम कंसिडर करते हैं B, जो कि जिसके कोऑर्डिनेट्स जो है तो वो x2 y2 हम मान लेते हैं. x2 y2 जो कि जिसका मास हमको पता है ऑलरेडी m2 है. सपोज m2 is the mass of this second particle, no doubt. Now let us try to join the line or draw a line joining these two particles here. तो इन दोनों particles को join करने वाला एक line हम बना लेंगे. ठीक है, so this is the line AB, and we already know that the center of mass of these two particles always divides the line joining these two particles in the inverse ratio of their masses. That means this C is going to be the particle or point on the line AB with the coordinates x and y. Suppose it is to such that the ratio of masses, ratio of the distances of C from A and B is actually going to be m2 is to m1. Okay, so that means ये जो है ये part m2 है. Ratio of distances of C from A and B is going to be m2 is to m1. That means this AC and CB is going to be in the ratio m2 is to m1. तो ये हमको यहाँ पे रखना सोचना है. तो अगर हम यहाँ पे इसको लिख देते हैं कि AC is to CB is going to be equal to m2 is to m1, and now we want to find out the coordinates of this point C, which divides the line AB in the ratio m2 is to m1. Now this becomes a very similar situation. ये भी एक बिल्कुल similar एक simple situation हो जाता है जो कि हमने I think so 10th standard में study की है already. You must have been seen that if suppose there are two particles in the xy plane with the coordinates x1 y1 and x2 y2 suppose, तो ये जो दो particles होते हैं x1 y1 और x2 y2, तो इनको m is to n इतने रेशियो में डिवाइड करने वाला जो पॉइंट है तो वो हमको सेक्शन फॉर्मूला से मिल जाता है. If suppose this A and B are the two points which are located at the coordinates x1 y1 and x2 y2, and we want to find out the coordinates of C, then there is a special formula which is called as the section formula, which is used like this. C will have the coordinates. So C के जो coordinates है तो वो अगर हमने मान लिया x और y, तो section formula tells us that this x coordinate of C can be obtained to be simply equal to m times of x2 plus n times of x1, that is to be whole divided by m plus n. If you remember, that means this m has to be multiplied with the x coordinate of B, and this n has to be multiplied with this x coordinate of A, and then they have to add up together. And the same thing we have to do it for the y coordinate also, so as to get the y coordinate of point C, which divides the line in ratio m is to n. So we can just do it in this way, that y will actually be equal to m into y2 plus n into y1, that is to be whole divided by m plus n as it is. And then we can just apply the same thing here. So this m2 has to be multiplied with x2 and m1 has to be multiplied with x1, because C divides the line joining AB in the ratio m2 is to m1, and that's why we can just get the x coordinate of the center of mass to be simply equal to m2 into x2 upon plus m1 into x1, and that is to be whole divided by m2 plus m1. That's it. And this is the y coordinate of center of mass, which can be similarly written to be simply equal to m2 into y2 plus m1 into y1, that is to be whole divided by m2 plus m1 in this way. So by seeing this formula, ये formula observe करने के बाद हमको ये पता चलता है कि the formula for center of mass, coordinate of center of mass is so symmetric that it can be generalized for number of particles also. That means we can just write this formula by changing slightly, as so here we can just write it as m1x1 plus m2x2 okay. So ये जो है ये टर्म्स सिर्फ उल्टा हम कर सकते हैं आराम से, तो उसको हम लिख सकते हैं m1x1 plus m2x2 upon m1 plus m2 in this way. And at the same time, y coordinate of center of mass can also be obtained to be simply equal to m1 y1 plus m2 y2, and that is to be divided by m1 plus m2 in this way. If suppose there are three particles, no problem. Again, we can just generalize this same formula for three particles also. For example, if we have the three particles in xy coordinate system, suppose this is the xy coordinate system, and suppose we have the 3 particles which are located at the points A, whose coordinate is x1, y1, suppose, and of mass m1. And suppose the B is another point whose coordinates are going to be x2, y2, and mass of this particle is going to be m2 here. And suppose this C is the new particle, third particle, which is having the coordinates x3, y3, and suppose its mass is given to be m3. Now we can just see that all these three particles will just have their center of mass located, देखो ये m1, m2 और m3, इन तीनों का जो सेंटर ऑफ मास होगा तो उसको हम अभी क्या नाम देंगे? Suppose G is going to be the center of mass. Here is the center of mass present, and the x coordinate of this center of mass is going to be, suppose, xcm, and the y coordinate of the center of mass is, suppose, going to be ycm. Okay. Yes. So there are formulae for finding this xcm and ycm. That means the center of mass के जो coordinates है तो वो हम simple तरीके से निकाल सकते हैं by just generalizing the above formulae. तो ऊपर जो हमने formula लिखे हैं वही हमको सिर्फ generalize करने हैं. तो देखो xcm, that means the x coordinate of center of mass can actually be obtained to be simply equal to, तो देखो इसमें numerator denominator होगा, and here in the numerator we can just have this m1 x1 plus m2 x2 plus m3 x3, that is to be whole divided by m1 plus m2 plus m3. That's it. So this is the formula for finding the center of mass of x coordinate system, x coordinate of center of mass. And in the same way, the y coordinate of center of mass can actually be obtained to be simply equal to m1 y1 plus m2 y2 plus m3 y3 and this has to be whole divided by the sum of masses, that is m1 plus m2 plus m3 here. So this is the formula for finding the center of mass of three particle system. तो देखो तीन particles का जो center of mass है तो वो निकालने के लिए हमारे पास formula है. That's it. And then we can just generalize this formula. Okay, one more thing we have to understand here is that we can just generalize this formula for three-dimensional coordinate system also. See here, if we just have this x-axis, y-axis, and z-axis also in addition to that. तो ये तीनों axis suppose हमारे पास है. देखो ठीक से. Suppose ये x-axis, y-axis और z-axis है और space के अंदर we have the three different particles whose coordinates are given by like A, whose coordinates are given as x1, y1. B is already there, whose coordinates are going to be x2, y2. Yes, and this third point particle is going to be C here, which is going to be having the coordinates. अब ये तीनों पार्टिकल स्पेस में है, स्पेस में मतलब किधर भी हो सकते हैं वो. तो its coordinate, sorry, every point will have three coordinates in that case, right? So x1, y1 and z1 will be the coordinates of this first point A, and obviously its mass is going to be m1. Okay, and suppose that this point is B, whose coordinates are given to be x2, y2, z2, and its mass is going to be m2 suppose, and the third one can be here like this. यहाँ पे किधर से भी हो सकता है वो, because it's 3-dimensional. So here the coordinates are x3, y3 and z3. The mass of this particle is going to be m3. Okay, so in that case the x coordinate of center of mass can again be found out by using the same formula which we already have it here. तो यहाँ पे जो हमको फॉर्मूले मिलते हैं तो वही हम यहाँ पे एज इट इज कॉपी कर सकते हैं आराम से. Yes, the same formula can be used here, and even for y coordinate also the same formula can be used here. वही फॉर्मूला हम यहाँ पे भी यूज कर सकते हैं बिल्कुल. But what about the z coordinate? तो z coordinate के लिए हम नया एक फॉर्मूला तैयार कर सकते हैं आराम से, which will be very similar to these previous two, and it will look like this. So we can just say that the z coordinate of center of mass, that means zcm, will be actually equal to m1 z1 plus m2 z2 plus m3 z3, and that is to be whole divided by m1 plus m2 plus m3 in this way. That means in general, if suppose we have 10 particles, then we can just continue this adding this product of m and x up to n times. तो यहाँ पे हम ये फॉर्मूला और जनरलाइज कर सकते हैं for n particles. We can just say that it will be m1x1 plus m2x2 plus m3x3 plus m4x4 m4x4 plus dash up to mnxn, where n is the number of particles, and we can just add this denominator में भी यहाँ पे m1 plus m2 plus m3 plus dash up to mn हमको ऐड करना है. The mass of nth particle has to be added here, and in the same way here also we can just continue this adding this product of mass of each particle and y coordinate of each particle, and last up to mn into yn, and this will actually be divided by the summation of masses of all the particles in this way. So here we can just get this mn, and last also here in this case dash up to mn, and in the numerator here you can just continue to add the product of sum of product of mass of each particle and the z coordinate of each particle up to nth in this way. So this becomes the formula for general formula for finding the z coordinate or xyz coordinates of number of particle system. So here we can just see, and even we can just write this formulae in a compact form. ये formula इसको compact form में लिखने के लिए हम क्या करेंगे? So we can make use of summation notation. If you have just seen it in the maths, that whenever there is a sum of n particles or sum of n terms, we can just express it as summation of mi into xi, where I is a variable which runs from 1 to n like this, and the denominator also can be expressed in terms of summation as the summation of mi's, where I is again a variable which runs from 1 to n in this way. And the same thing can be done here for this y coordinate also and z coordinate also. For just the sake of simplicity, we can just write it as summation of my and divided by summation of m. And here also in the we can, for z coordinate, we can just write it in the short summation of mz divided by summation of m. Here we can understand that the summation of mz means the sum of product of mass of each particle and the z coordinate of that corresponding particle, and that is to be divided by the summation of all particles, masses of all particles. See, the sum of masses of all the particles will become the total mass of the body itself, and hence we can sometimes replace it by capital M. If the total mass of the body is known, then we can just replace this summation of M by simply capital M. That is the total mass of the body. Yes, so that this is what I want to tell. See, we have these three different vectors, one of which is joining the particle A here. So we can just denote it by R1 bar. Okay, ये वेक्टर जो है, इस वेक्टर को हम बोल देंगे R1 bar. Okay, this is your R1 bar. And the second vector, you can just draw it here, joining the point B here. So B को join करने वाला जो वेक्टर है, तो उसको हम बोल देंगे R2 bar. So we can just draw the position vector of each of these particles which join the origin to that particular particle. So this is R2 bar, we can say. And the third vector can also be drawn here, which joins the origin with the point C here. ये C particle को join करने वाला एक तीसरा vector हम draw करेंगे यहाँ पे, जिसको हम बोल सकते हैं R3 bar. And in the same way, we can just continue to draw the vectors joining all these particles, whichever is present. जितने भी particles present है वहाँ पे, उन सभी particles को join करने वाले एक एक vector हम यहाँ पे draw कर सकते हैं आराम से. And then we can just be able to find out the position vector of that center of mass. Suppose the center of mass is present at this point, particularly here. ये हमारा center of mass suppose है. Okay, so the vector, position vector of this center of mass can be supposed to be RCM. See here, this is the RCM bar. So how to find out this RCM bar is, तो उसके लिए यही formula हम use कर सकते हैं, because we can just have this center of mass of the first particle. The position vector of the first particle, that is R1 bar, can actually be expressed as X1 I bar plus Y1 J bar plus Z1 into K bar, correct hai? So this is the position vector of this first particle, that is A particle, whose mass is M1. And for the second particle, its position vector can be expressed in terms of X, Y, Z in this way, that is X2 into I bar plus Y2 into J bar plus, here it is Z2 into K bar. Yes. And then we can be able to get the position vector of this third particle also. So R3 bar can be expressed in terms of XYZ as X3 into I bar plus Y3 into J bar and Z3 into K bar. Okay, so these are the position vectors of all these particles. Even we can continue for nth particle here. So nth particle का जो position vector है, तो वो भी हमको इसी तरह से मिलने वाला है. That is xn I bar plus, here it will be yn into j bar and finally Zn into k bar. Correct है? So in this case we have obtained the position vectors of all these particles, and then we can be able to use this formula. जो फॉर्मूला हमने x कोऑर्डिनेट, y कोऑर्डिनेट या z कोऑर्डिनेट निकालने के लिए किया है, यूज किया है, वही फॉर्मूला हम, वैसा ही सिमिलर फॉर्मूला हम बना सकते हैं पोजीशन वेक्टर्स के लिए. So we can just in general say that the position vector of center of mass, that is RCM bar, is actually going to be equal to, तो यहाँ पे न्यूमरेटर में क्या आएगा तो हम देख सकते हैं. So it will be m1 into r1 bar. Okay, m1 into r1 bar, mass of the first particle into its position vector, no doubt, plus the second particle का mass m2 into उसका खुद का position vector r2 bar, plus m3 into r3 bar, and so on up to nth, and then we have to divide it by m1 plus m2 plus m3 in this way. अब यहाँ पे तो चलो तीन ही पार्टिकल्स है इसलिए हमने तीन तक ही एक्सटेंड किया, but we can just generalize this formula and extend it up to n particles also, and just write it in compact form in this way also. So इसको हम plus delta dash up to mn into rn bar ऐसा भी एक्सप्रेस कर सकते हैं. और यहाँ पे अकॉर्डिंगली नीचे जो है तो यहाँ पे भी प्लस डेल्टा अप टू mn आ जाएगा बिल्कुल. And we can just write this formula in compact form in terms of summation as summation of mi into ri bar, as I runs from 1 to n, and that is to be whole divided by capital M, where capital M supposed to be the total mass of this whole body. तो इस पूरे बॉडी का मास अगर हम मान लेते हैं कैपिटल M है तो उस केस में ये फॉर्मूला हमको मिलेगा as the final formula for the finding the position vector of n particle system. Okay, and even no doubt we can just convert this formulae into these three formulae whenever required. जब चाहे तब हम यहाँ पे ये फॉर्मूले डिराइव कर सकते हैं. अगर हम एक्स वाई कोऑर्डिनेट्स या आई बार जे बार के बार के कोएफिशिएंट्स अगर इक्वेट करेंगे ना तो उससे हमको ये फॉर्मूलेस को यूज करके हम ये फॉर्मूलेस भी डिराइव कर सकते हैं बिल्कुल. सो दिस इज गोइंग टू बी द मोस्ट जनरल फॉर्मूला for the center of mass, position vector of center of mass, remember. But here one thing is to be remembered here, that if all these formulae can be used only when the body consists of number of finite particles. बॉडी के अंदर जब अलग अलग पार्टिकल्स हैं जिनको हम गिन सकते हैं, and we can just separately count them like 1 2 3 4, then in that case these formulae are okay. But if suppose the body consists of infinite number of particles which are closely related with each other, just like a suppose for example there is a body in this way, एक homogeneous body है, imagine करो, इसका shape irregular है, we don't know how it is, but we want to find out the center of mass of this body. But here the problem here is that the body consists of large number of particles, and these particles are so close to each other that there is no difference between one particle and another one here. That means we can just shade this body in this way. तो ये पूरा जो body है इसको हम अंदर, तो इसके अंदर के जो particles है इसको हम इस तरह से शेड कर सकते हैं और बोल सकते हैं कि there are infinite number of particles already present there in this body, which we cannot distinguish actually. यहाँ पे हम डिस्टिंग्विश नहीं कर सकते कि एक पार्टिकल को दूसरे पार्टिकल से अलग नहीं कर सकते हैं, and neither we can find out their coordinates nor we can just find out their masses separately. तो एक पार्टिकल कहाँ पे चालू होता है और दूसरा पार्टिकल कहाँ पे खत्म होता है और दूसरा पार्टिकल कहाँ से चालू होता है ये पता ही नहीं चलता है. That is called as a homogeneous body, just like a metal sphere or just like a metal disc, और मेटल का बना हुआ कोई भी शेप का जो बॉडी होता है उसको हम इस तरह से कंसिडर कर सकते हैं, which is actually made up of large number of infinite number of particles. And in this case, what we have to do, how to find out the center of mass, position of center of mass here in this case. So in this case, the location of center of mass can be found out by considering the any one particle, one element of this body here. एक element हम यहाँ पे imagine करते हैं, जिसको हम मान लेते हैं dm, उसका mass dm मान लेते हैं, और उसका जो distance है या location है, यहाँ पे हम इसको r मान लेते हैं, r bar. So in that case, the position vector of center of mass, that is r cm bar, can actually be obtained by just integration of, तो यहाँ पे जो समेशन था, तो समेशन के बदले यहाँ पे क्या आने वाला है, इंटीग्रेशन आने वाला है. हमारा जो फॉर्मूला था अभी जो हमने डिराइव किया था वो है इस तरह से, r cm bar is actually equal to summation of mi bar, mi into ri bar, correct है, and that is divided by summation of mi bar, mi, ये हमको फॉर्मूला मिला था. तो अभी आपको क्या करना है कि ये समेशन जो है, summation has to be replaced by integration, just because there are not finite number of particles, but there are infinite number of particles going to be there, and that's why the summation sign will just be replaced by the integration sign. So here we can just carry out integration of r bar into dm, and that is to be divided by integration of simply dm, which can also be considered as capital M. So ये जो डिनोमिनेटर में हम टोटल बॉडी का मास रख सकते हैं, but the integration of r bar dm has to be carried out, and even we can just say this r bar can be expressed as xi bar plus yj bar plus zk bar. So if we just suppose this rcm bar को भी अगर हम separately express करते हैं इस तरह से कि xcm into I bar plus ycm, that is the y coordinate of center of mass, into j bar, which is going to be equal to zcm, that is z coordinate of center of mass, into k bar. Then that will be actually equal to the, अभी देखो यहाँ पे, this whole thing has to be divided by capital M, no doubt, that is the total mass of the body. And this r bar can also be split up in three terms, like integration of xi bar plus yj bar plus z into k bar, and that is to be multiplied with dm in this way. And then we can just solve this further. तो 2 मिनट में इसको हम सिंप्लीफाई करेंगे. देखो ठीक से, ये जो है ये पार्ट हम एज इट इज कॉपी करेंगे नीचे, बट हियर इस न्यूमरेटर वाला जो पार्ट है तो वो हम थोड़ा सा स्प्लिट करेंगे. ये dm जो है, दिस dm will just be multiplied to each of these terms inside, so that we can just have these three terms, and also this integration will be separated for all these three terms inside, so that we can just get these three terms like this: integration of x into dm into I bar, that is to be divided by m, correct है, ये बनेगा m. फिर यहाँ पे plus, we can just put this in the bracket, and here we can just get this second term to be simply integration of y dm, that is to be divided by capital M, that is multiplied with j bar, and here plus integration of z into dm, once again, that is to be divided by capital M, and again it is multiplied with k bar. Now we can just understand that if we just compare the coefficient of I bar here on the array LHS, तो LHS में I bar का coefficient कौन है, xcm है, जो कि यहाँ पे RHS में ये पूरा है. We can just compare them. Again, we can just compare the coefficient of j bar on LHS, which is ycm, and it has to be compared with coefficient of j bar on RHS, which is going to be ycm, integration of y dm upon capital M here. And similarly, we can just compare the coefficient of k bar also on LHS as well as RHS. So as to get these three different formulae, which you can just obtain it as, तो ये तीन फॉर्मूले हमको इस तरह से मिल सकते हैं आराम से. तो सबसे पहला फॉर्मूला हमको मिलेगा XCM के लिए. So the coordinate of x coordinate of center of mass can actually be obtained to be equal to integration of x into dm upon capital M. Then the y coordinate of center of mass can actually be obtained to be simply integration of y dm upon capital M. And in the same way, here the z coordinate of this center of mass can also be obtained, that is ZCM, which is going to be actually integration of z into dm, that is to be divided by capital M. That's it. So these are the three formulae which are going to be for the x, y, z coordinates of center of mass in case of a homogeneous body. Okay, homogeneous body in which the two particles can never be separated from each other, and we can never know where the first particle just ends and next particle just starts. So the particles are just closely distributed in such a way that there is no gap at all. Basically दो particles के बीच में कोई gap होता ही नहीं है, और ऐसे केस में हमको ये वाले फॉर्मूले यूज करने पड़ते हैं in order to find out the location of center of mass in such a case. Remember, okay. And using this formula, we can just prove that the center of mass of different coordinates, मतलब जो अलग अलग center of mass होते हैं अलग अलग shapes के, तो वो तुमको already टेक्स्ट बुक के अंदर दिए हुए. Just go through it. There is a table given in the textbook. I will just show that here. Okay, you can just see the screen now. Yes, ये आपका टेक्स्ट बुक है. ओके, तो इसमें अभी हमने जो फॉर्मूले देखे, तो okay, see here, these are some formulae for center of mass, coordinates of center of mass. तो ये हमने ऑलरेडी अभी देखा. X coordinate of center of mass, Y coordinate of center of mass, and Z coordinate of center of mass can be found out. And here is discussed about the continuous mass distribution. If the uniform density का कोई भी body अगर है जिसका mass continuously distributed है, that means there are infinite number of particles which cannot be separated from each other. Then in that case, we can just see the formula for center of mass. X coordinate of the center of mass can be obtained to be integration of x dm upon capital M. In the same way, y and z coordinates can also be obtained. And based on this formula, integration formula, we can just have the formula for the center of mass of different systems like isosceles triangular plate, whose height is capital H, lies at h/3 distance from the below, from the bottom point. तो ये bottom point से 1/3 height पे वो center of mass lie करता है isosceles triangular plate का. Then again, right angle triangular plate अगर है तो उसके अगर दोनों sides हमको पता है, तो center of mass of that such a right angle triangle plate lies at p/3 q/3 coordinates. मतलब x coordinate of center of mass will be p/3, where p is going to be the side along x-axis, and y coordinate of center of mass will actually be q by 3, where the q is going to be the side of the right angle triangle along y-axis. In the same way, the thin semicircular ring of radius r has its center of mass located along the diameter, passing through its center and perpendicular to its cut base, and at a distance 2r by pi from the center of this ring. तो इस रिंग का जो सेंटर ऑफ मास होता है वो 2r by pi ने डिस्टेंस ऊपर होता है. Similarly, if it is a disk, semicircular disk of radius r, then its center of mass also lies on the same vertical line on y-axis, but at a distance of 4r by 3 pi from the center. All these formulae can be proved basically by using the technique of integration, which you have just seen. यहाँ पे जो हमने फॉर्मूले देखे कि नहीं, यहाँ पे ये जो x कोऑर्डिनेट, y कोऑर्डिनेट और z कोऑर्डिनेट ढूंढ के निकालने का जो फॉर्मूला हमने देखा, उसको यूज करके ही हम ये सारे फॉर्मूले प्रूव कर सकते हैं एक्चुअली. इवन यहाँ पे भी हेमिस्फेरिकल शेल जो होता है, hemispherical shell of radius r has its center of mass located at a distance r by 2, where r is going to be the radius of that shell. Shell मतलब sphere, ठीक है, hemisphere, hollow sphere you can say. And if suppose there is a solid hemisphere, तो solid sphere अगर है वो, तो उसका आधा पार्ट अगर है, तो उस आधे पार्ट का center of mass उसके diameter along ही lie करेगा, लेकिन at what distance it lies is 3r by 8 distance above the center. If again the hollow right circular cone जो होता है, hollow cone, तो उसका जो center of mass है वो हमेशा h by 3 इतना distance ऊपर हुआ करता है. This is the location of center of mass, where h is going to be the total height of this cone. In the same way here, if suppose there is a solid cone, तो ये solid cone है जिसका height h है, तो उसका center of mass हमेशा h by 4 distance ऊपर हुआ करता है. All these formulae are to be learned as it is. Okay, no proof will be given. If any one of you want the proof, then you can go through HC Verma or the reference books for JE and Neet, in which that proof is discussed in detail. Actually, we need not to discuss it in the regular session, but we'll just do it in the when we'll work out the JE Neet session of this chapter later on. And one more thing is that in order to find out the center of mass of cut part, ये एक थोड़ा सा बड़ा टॉपिक है. Let us continue this in the next lecture. Okay, everything else is done in this chapter. Only the method of finding the center of mass of cut part is to be remembered. Yes, remainder. That is, we have to do it in the next lecture. Okay, so tomorrow's lecture we can just do that only. Yes, let us stop this lecture here. Thank you all of you.